In this section, we'll be discussing some problem-solving strategies and talking about it in theory and then seeing it in practice a little bit. So Polya's problem-solving strategy is four-step problem-solving strategy consists of the following four steps. First, understand the problem. It's a very overlooked step usually, but just, do you understand everything that's going into the problem? Can you restate it in your own words, etc.? Step two, devise a plan. Figure out like what your strategy is going to be. Once you get that down, then you want to carry out that plan. And then review the solution. Okay, so understand, devise a plan, carry out the plan, review the solution. Look back. So as I said, understanding the problem is usually the most overlooked part of Polya's four steps. And so, what goes into this? So can you restate the problem in your own words? What do you know about these types of problems? Have you seen similar problems before? Can you sort of generalize some tools and techniques that you did in other similar problems to whatever you're working on now? Is there any missing information that would help you solve the problem? Sometimes it might seem like you don't have enough information to solve the problem if the problem is just handed to you, but it might be like, oh, if only I just knew this one key little fact. Well, maybe you can actually work your way towards showing that key fact is true or something, and then once you get that, then that can help you complete the problem from there. So that sort of builds intermediate steps for you. Conversely, maybe they're giving you too much information. Maybe there's some information that's just really not helpful to the problem. Understanding the goal is often the most important part of this. That's why I sort of emphasize it here. But this goes deeper than just knowing I'm just looking for the answer. What does your solution what is your solution inevitably going to kind of look like? Is your solution just going to be a number? Is it going to be a sequence of steps that you have to take? What is the end, your end solution going to ultimately kind of look like, other than, obviously just a number, but how are you going to get there? For devising a plan, there are some commonly used procedures for coming up with your plan. Making a list of all the known info can be helpful if you're just trying to organize your thoughts. Make a list of the info that is needed to solve the problem. So, you have your known stuff and then your stuff which you kind of need to figure out in the problem. That just kind of helps you organize your thoughts a little bit more. Drawing a picture or a diagram is often a step that I see students neglect. That is incredibly important. I've been studying math for I guess decades now, and still to this day, drawing a picture or a diagram is just one of the most important things that I can do in solving certain types of problems. So I never skip that kind of step if it's there. Making an organized list showing all possibilities with emphasis on the word organized. So if you're for example, saying all right, well, how many ways are there to break $1 into coins? If I'm asking how many ways are there to break $1 into coins, you could just be okay, well, I could do 100 pennies, I could do 20 nickels, I could do 4 quarters, I could do 10 dimes, or I could do 2 quarters and 50 pennies, and you could just kind of keep listing them like that. But that's a really bad approach, because you're not listing them in any sort of order that makes it easy to keep track of all of the possibilities. So like the easiest way you could maybe do that would be, let me, oh, come on. I could do like, 25, 25, 25, 25. I could do 4 quarters. I could do 3 quarters and then see, all right, well, how many ways are there to break that remaining 25 cents up? And that could take the place of, so I'll always just use the biggest possible coins that I can make there. So the next biggest coin would be a dime. Then from there, I would do another dime and then a nickel. Maybe I would do 2 dimes and 5 pennies. Or maybe I would do a dime, 2 nickels, or 3 nickels, I guess, if I'm going in decreasing order. And then 2 nickels and 5 pennies, 1 nickel and 10 pennies, just going in order. And obviously every time I'm still doing like the 3 quarters, etc. But you see there's like an organization to this list of I'm, using the biggest coins that I possibly can. And then like at the very end of it, once I can no longer fit any more like dimes, then I go down to nickels. Once I've already used that possibility, then I go down to pennies and so on. Okay. Similar is making a table or a chart. We'll see examples of that today. Solving a simpler version of the problem first. This is a hugely useful tool that you could do. Looking for pattern, we've already seen stuff like that with like sequences and lists. Working backwards, we'll see an example like that today as well. Introduce variables and or write an equation. A lot of times students are kind of hesitant to create their own variables in problems, but creating your own variables can be just hugely useful. It has a lot of benefits in a lot of situations. Sometimes you can make an equation out of it, sometimes you can't. We've already seen like the number trick that we did in one of the previous videos, where you start with a number, add 6, multiply by 3, etc., and then you get to like the number 2 at the end, whatever the steps were. Like we introduced the variable, just like call that initial number x and then apply those steps of like 3x and then add 6 and then divide by 3 and subtract your original number, you get to 2, etc. If we didn't introduce that variable at the beginning, that problem would have been a lot harder. And this list just like goes on and on. This is like the devising a plan, blah, blah, blah. So there are just like so many things that could kind of go into this step. Step 3, carry out the plan. This one's like kind of straightforward. Once you have figured out what your plan is going to be, once you have the plan, just do it. Some important things that students don't always really do is make sure that your work is easy to follow. This is incredibly important, not only for like, whoever's like grading your work or something like that. I'm not really going to do a lot of grading for this specific class because everything's going to be graded like online, like automatically, but I still recommend making your work easy to follow. Not only is it beneficial to you for being able to look back on your work and being like, okay, what did I do here? Like like your work then becomes like a good study tool. It also helps you organize your thoughts a little bit better if you're making your work easy to follow. Like if you're just trying to get the problem done as fast as possible, you're probably not going to get as much out of that process as if you were to make everything like really neat and organized. Making your solution neat and organized, like your brain is just going to process it a little bit differently. And then once you get into like the professional world, if your work is not easy to follow, your coworkers are just not going to want to work with you. If you can't like explain like what you're doing to somebody else, like that makes you way less valuable compared to someone who is able to do the same things as you, but also explain what they're doing, why they're doing it, how they're doing it, and what's important about it. Also, sometimes your initial plan is not going to work. Let's go back to that list. That list of devising a plan is massive. There are so many things that you could do. You think that making the table or a chart is going to be like the best thing that you could do, and then you do it and it's not useful at all, that's fine. You tried something that you learned that doesn't work, and then you try something else and you just keep pushing forward. And that is fine. Just be flexible and keep trying, keep pushing forward, and eventually you'll get there. You'll just keep learning along the way. Learning that something doesn't work is still valuable. Okay, review the solution. Once you find the solution, check it. Ensure that solution is consistent with all the facts of the problem. If you solved an equation, 2x plus 5 is equal to 9, and you find that x is equal to 3. If you were to plug x equals 3 back into this equation, you get 2 times 3 plus 5. Is that actually equal to 9? Like, oh no, I'm not getting 9. So that's not consistent with the facts of the problem, and that would tell you that you messed up something along the way. That kind of gives you valuable information. Can you interpret the solution in the context of the problem? If, in the previous like equation problem, like that's not really going to make as much sense. But if you have like a problem where you're solving for, what is the temperature going to be in the middle of the afternoon, and your answer comes out to be like 700 degrees Celsius, like chances are you probably did something wrong. Or something, maybe the problem was just messed up, but just try and make sure that like everything is making good sense in the context of the problem. In terms of building your problem solving skills and getting you ready to do like similar problems, ask yourself how or whether this solution could apply to other similar or more involved problems. If you can see a solution and be like, oh yeah, this would be like really useful for something like this. Oh, if this problem was tweaked in this sort of way, then all I would have to do is, change this, this, and this in my solution, and that would allow me to do this. That's just going to build your problem solving toolkit, and you'll just be better because of it. So let's see a couple of problems and specific examples of that giant list that we built of problem-solving strategies. So here we have a Mortal Kombat tournament. It's just a video game consisting of the tournament has 12 players, and every player must play each other 3 times. How many games must be played? So if you were to solve this normally, you might start by just drawing 12 people. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. I think I did 12. Yeah, that looks good. Okay, so if you were to start counting how many times that they must play each other, well, you could just assume that they're playing each other once, and then multiply that final answer by 3. And if each player plays each other once, you just have to say, all right, well these 2 guys are going to play, these 2 guys will play, these 2 will play, these 2 will play, these 2 will play. Just kind of keep doing this. You just kind of draw a line for each of those. So this player will be involved with, well, there are 11 other players. So this player right here will be involved in 11 matches. Okay. Then you have to do that for player 2 as well. So player 2, play this guy, and this guy, and this guy, and this guy, and this guy. And you can kind of keep doing this, but very quickly you can see that like this diagram is going to get super, super complicated, right? So what we could do instead is solve a simpler version of the problem and maybe hope to extend that. So let's say that instead of 12 players, we had, all right, well, you don't want to make it too easy because then it's just kind of hard to generalize. So let's do like 2 players. If there are 2 players, how many games must be played? Well, they both play each other 3 times, and so there's going to be just a total of 3 games. That we solved it, but that doesn't really help us very much. So we have to make it simpler, but not too much simpler, so that we can still, get something from it, and maybe use some sort of reasoning to, say like, oh, well, it fit like this sort of formula here. Maybe it fits a formula for like extending it to 12 players. So let's do it for, say, 4 and see what happens. Okay, so if there are 4, what I have to do is just draw a line between every 2 pairs of players. And if I do that, what do we see? Well, we see player 1, there are 3 lines to be drawn. Player 2, there are 2 more lines to be drawn. And then player 3, there's 1 more line to be drawn. And so we can just kind of count the number of lines right there. So there's 3 plus 2 plus 1, which is equal to 6. So we have 3 lines plus 2 lines plus 1 line, like so. Okay, so we get 6 for 4 players. What if we do 6? Okay, let's do it. Let me do this. Okay, so this will be player 1 over here. And then player 1 will have to play... Oh, also I forgot over here to multiply our final answer by 3. So we get 18. Okay, over here, player 1 has to play the other 5 players. Player 2 has to then, so they've already played player 1, so they'll play player 2, player 3, 4, 3, 4, 5, and 6. So that's 4 more. So just keeping track, player 1 had 5 matches, times 3 in the end. Player 2, there are 4 more matches to be had because they already played player 1. Player 3, there are 3 more matches to be had. The next player, there's only going to be 2 more matches. And then the next player, there's only going to be 1 more match. And then by that point, the last player has already played everybody there. 5 plus 4 plus 3 plus 2 plus 1. So we're starting to kind of see a pattern here. So what's this equal to? 10, 15. So then 15 times 3 is equal to 45 total matches. Okay, so maybe at this point you can kind of notice a pattern. So if there are 4 players, then we have 3 plus 2 plus 1. If there are 6 players, then we would have 5 plus 4 plus 3 plus 2 plus 1. If we were to have 10 players, then how many matches would we have? Well, it would be 9 plus 8 plus 7 plus etc. all the way down to like plus 2 plus 1, right? I don't want to write all that out. But, if we have 6 players, it starts at 5. If we have 4 players, it starts at 3. If we have 10 players, it should start at n. And if we have n players, then we would do n minus 1 plus n minus 2 plus n minus 3 plus all the way down to plus 2 plus 1. Okay. Well, we've actually seen something like this before. This is where we could say, well, if this is a sub n, then if I were to double a sub n, so I could reverse the order here. So start with plus 1, and then plus 2, and then plus 3, and then up to n minus 2, and then n minus 1 is where we end. And then if we were to add those two lists together, we're basically just doubling a sub n, the number of matches here, which at the end will multiply by 3. Then, n minus 1 plus 1, that equals n. Same for n minus 2 plus 2, that equals n. And then all the way down here, that's plus n. That's plus n. So we're just adding n a bunch of times. How many times are we adding it? Well, 1, 2, 3, 4, 5, 6. We end up at n minus 1. So this is n times n minus 1, which is equal to 2 times a sub n. So a sub n would be equal to n times n minus 1 over 2. And so now, at this point, we can just answer the final question of like how many games are going to be played here. Oh, and by the way, this answer we should also just go ahead and multiply it by 3 because, again, each player must play each other 3 times. Like over here with just this, we're just assuming that they're playing each other once, and then, that's a simpler version of the problem. And then we ramp it back up by just multiplying by 3. So then for 12 players, there would be 3 times 12 times 12 minus 1, which is 11, all over 2. So this many games. What is that equal to? Okay, so 3 times 12 times 11. I can take like 12 to make that a 6. 3 times 6 times 11. That's the same as like 3 times 66. It's 180 plus 18. That is 198 games, I believe, if I'm doing my arithmetic correctly in my head. Okay, so 198 games. All right, what about making an organized list? How can we use that? So similar to that like coin problem. So let's say that Suji is attempting a true-false quiz with 5 questions. How many possible ways are there for Suji to complete the quiz by answering true for exactly 2 of the questions? So this is one of those ones where you actually like really want to make sure that you're understanding the problem first. Does this mean that like the first 2 questions have to be true? Does it mean that like, the first, is it telling you anything about the other ones? Like, what if I do true, true, and then false, false, true? Does that count? Well, no, because it's saying it has to be exactly 2 of the questions. So, let's, what would some possible test answers look like? Well, you could do true, true, and then false, false, false. You could do true, false, true, and then the other 2 have to be false. And then, kind of keep going like that. So I would recommend at this point for you to pause the video and see if you could write down an organized list of all of the possibilities and make it so that the organization of your list makes it obvious that there are no other possibilities. And then, just count your possibilities and then there's your answer. All right, did you pause the video and try it? I'm hoping you did. So here, what I'm going to do, how I'm going to organize this is have the true answers be the ones that are like, I'm answering them as early as possible. So if I'm answering them as early as possible, then that means, for now, my first answer has to always be true until I run out of possibilities for that. So first one's true, second one's true. Okay, cool. Well, what if the second one is not true? So it's false. Well, let's make the next one true. Well, what if that one's also not true? Then we would have true, false, false, true, and false. And then, of course, I could keep going. Maybe that one is also false. Then this one would be true. Okay, well, what if this one is not true? Well, then what? Well, at this point, we kind of have run out of possibilities where the first option is true. So let's stop writing down examples where that first answer is true. Let's just switch to making that one be false. So that one's false. Let's make the second one true. So no matter what I write here, this is not going to be repeated in the above list because that first answer is false, which is different from everything else. So let's make the third answer be true, and then false, false. Let's keep that second answer be true for as long as we can. Third answer, let's change that to false, and then make true be the fourth answer. And then the fifth answer. And then at this point, we've run out of possibilities for when the second one is true and the first one is false. Okay, let's move over here. So let's say that the first two are false now. Okay, and then again, notice that none of these possibilities will be repeated in the first table because true shows up as one of the first two options for everything that we've wrote down so far. So we'll have false, false, and then let's make our next two be true. And then we'll do false, false, and then we'll keep that third answer to be true, and then make that next one be false instead, and then end with true. And, whoa, go away. And then we run out of options where we have false, false, true, so we'll have to do false, 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 and then this next one has to be true, and then the next one has to be true. And at this point, now I think we've run out of options to write down, because if we make that fourth answer be false, I mean, sure, we can make the fifth answer be true, but we just don't have enough spots to put two true answers for this test now. So let's actually move this down here. Let's organize our list a little bit better. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total options. And because of how we organized our list, we can confidently say that there are 10 possibilities. Okay, making a table / looking for a pattern. So let's determine the ones digit of the number 2 to the power of 123. So first instinct might be to plug 2 to the 123 into your calculator, but this number is just going to be so massive, so huge, that it's not going to be able to display the ones digit for you, most likely. Most basic calculators will not be able to do that for you. So what we'll do instead is look at smaller examples first, and then maybe see from examining the smaller examples if we can find a pattern that helps us generalize. So if I were to do, let's do a table of like 2 to the n, and then actually let's say make a table for ones digit of 2 to the n for various powers of n. So we'll do n, we'll do 2 to the n, and then we'll do the ones digit. So this is going to be a table with like 3 columns here. So if my power is 1, then 2 to the 1 is just equal to 2. So of course the ones digit will also be 2. If my power is 2, 2 to the power of 2 is equal to 4. That's going to be my ones digit. 2 to the power of 3 is equal to 8. 2 to the power of 4, 2, 4, 8, 16. So my ones digit now is 6. 2 to the 5. 16 times 2 is 32, so my ones digit is 2. 2 to the 6, that's 64. So my ones digit is 4. 2 to the 7, that's 128. These numbers are starting to get pretty big, so hopefully we can find a pattern soon. 2 to the 8 is 256, so that brings us to a 6 there. Let's extend this table over here, except maybe let's get rid of that, that 2 to the n column. Let's maybe just do n, and then look at the ones digit. Okay. All right, well, if I were to do, let's copy 7 and 8 back here. So 7 and 8 had a ones digit of like 8 and then 6, and then 9. Well, I don't even need to know like what comes before that ones digit, because if I were to take this number and just, you know, just has some stuff to the left of it, and if I were to multiply this by 2, then what would the new ones digit be? Well, the new ones digit would just be a 2, right? And then this number right here, if I were to take this number whose ones digit is 2 and then double it, multiply it by 2, what would my new ones digit be? It would be 4. And then a power of 11 will give me a ones digit of 4 times 2 is 8. And then a power of 12, take a number that ends in an 8 and then double it. I'm going to get a number that ends in a 6. Take a number that ends in a 6 and double it, you get a 2. Ends in a 2, should get a 4. And then you'll get an 8. And at this point, we should see a pattern emerging. So our ones digit goes 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6. And it should just kind of keep going. Let's get rid of those just to avoid redundancy. So we already have n equals 8 over there. Oops. Okay, so every 4, the ones digit just keeps repeating. And so we're just going to kind of roll with that pattern, and it's like, it should make sense too why the pattern is repeating, because we're using the same logic every time. You know, if the ones digit is 2 and you double that number, you're going to get a number whose ones digit is 4. Like, that logic is sound. We're not really making any like leaps of faith here. We're just kind of logicking our way to this conclusion that every 4 the ones digit is just going to repeat. All right, well, what about 2 to the 123? Well, we just gotta kind of figure out where 123 would lie in this table. And so every 4, it's going to repeat. So let's say, let's see, how do I explain this? Okay, so if I were to do 2 to the 1, 2 to the 5th, 2 to the 9th, 2 to the 13th, 2 to the 17th. These numbers are all going to have the same ones digit, because this just means I'm increasing my power by like 4, and I'm just going to go, I'm repeating the ones digit every 4, so yeah. Okay, so I could just kind of keep doing this until I get to something that's like kind of close to 123. If I were to do that, well, okay, so you can see that like 120 is a multiple of 4. So if I were to do this, but for like 2 to the 4th, and then 2 to the 8th, 2 to the 12th, 2 to the 16th, eventually I would get 2 to the 120th. And what would the ones digit be for that? Well, the ones digit for 2 to the 4 is 6. So these numbers would all have a ones digit of 6. And then I could just count off from here. 121, 122, and then 123. So 6, double that, I'll get to a ones digit of 2. Double that, I get to a ones digit of 4. Double that, I get to a ones digit of 8. So our final answer should be a ones digit of 8. All right. Here's another one where we're gonna do some working backwards. So Ha-Jun is on a bit of a spending spree. He spends $600 on a new coat. Then he loses half of his remaining money gambling. He then gets a $1,000 paycheck before spending $100 of it on a nice dinner. If Ha-Jun is now left with $2,600, how much did Ha-Jun start with? Okay, so one thing that you could do is introduce a variable. And this will work fine. So if you just say X is like however much money Ha-Jun started with, you could just follow this procedure and then get down to say like, all right, well, he spent 600, so then you're at X minus 600, and then do stuff, and then eventually you get some expression, and then just set it equal to 2,600, and then solve for X. But that sounds like very like algebraically complicated, when we could just work backwards to make this problem a little bit easier. So Ha-Jun has 2,600 right now. Right before he had 2,600, he spent $100 of it on a dinner. So before he bought the dinner, he was at 2,700. Then he spent 100 of it, and then that's where he was. Before he bought that dinner, he got a paycheck. He had a $1,000 paycheck. So before that, he actually had $1,000 less than he had at the start of that dinner. So he was at 1,700, gains 1,000. He's at 2,700. So I just subtracted 1,000, working backwards to get what he had before that paycheck. Before that, he lost half of his remaining money gambling. That was what happened before the paycheck. So he's at 1,700. If before that he lost half of his money gambling, then how much did he have before this? Well, he had double this. What's double 1,700? It's 3,400. So if he lost half of it, going from here to here, then to go from here to here, you double it. And then to finish this off, he spent $600 on a new coat. So if he had 3,400, before that he had 600 more. So he had 4,000 to begin with. Okay, I'm going to do one more bonus question, which is another solving a simpler version of the problem. This is one of, if not like my favorite like math problems that I've ever seen. I just think that like the solution is just like so simple and like so obvious, but your initial instinct is not always necessarily like that nice solution. Okay, so March Madness. So every March they have like this 128 single elimination basketball tournament. Okay, so how many games must be played in this tournament? So in the tournament, they will they'll usually just bracket it off. And I think that it's not exactly 128 anymore. I think they have like wild cards, but it doesn't really matter for the sake of the problem. So if you have like a 4-person tournament, and it would look something like this, right? Like you would have like team 1 versus team 4, and then team 2 versus team 3, and then the winners would like go in the final. Maybe you'd have like 1 versus 3. So you would have like 1 match here, 1 match here, and then 1 match here. So you'd have three games like so. Okay, so most people's like um, initial like thought for how to solve this problem would be like do it by round. So in the first round, you do 64 games, just like splitting this in half. So you do 64 games, and then that cuts down the number of teams in half. So now you have 64 teams after those 64 games. Then you play, um, divide those 64 teams into groups of two to play 32 games. And then that'll cut the total down to 32 teams. Do that again, plus 16 games, and then another 8 games, another 4 games, another 2 games, and then one more game for the final. So you could totally do this, and this solution is perfectly fine. If you add these numbers up, you'll get 127. What you might notice is that 127 is one less than 128. When we had a 4-person tournament, we also had one less than 4 number of games. We had 3 games to be played. And if you did this for like a 317 team tournament, like what would you get for that as well? So you wouldn't even like necessarily be able to do it in the same sort of way. So if you had 317 teams, you'd have to have like some like wild card teams, or like some teams that like have a first round bye or a second round bye even, and like the setup would just be like really confusing. So the much better way to like think about this is actually just do it as follows. So okay, every game that you play, one team goes home, right? If you have 317 teams, well, 316 of those teams have to eventually lose, except for, that's just like all of them except for whoever wins. And if one team loses every game and you need 316 teams to lose eventually, then that just means that there has to be 316 games that need to be played. And so you don't even have to do like that weird bracketing thing at all. It's just like totally inefficient and totally unnecessary. You just don't have to do it. If there are 128 teams, then there's just going to be a one less than that number of games. And that applies to no matter how many teams there are. It does not matter how you structure the tournament. This is going to be the number of games that need to be played.